Okay, good evening, ma'am. My name is Ope Daniel. Um, this is my project for the word spotting project. This is my second version. My first one had a bit of issues, so I now made a new one. So I'll be diving straight into it. So first of all, we go to the data acquisition. So what I did was I had a 3 minute sample. So first of all, I recorded a 3 minute sample with about 92 samples inside, 91 samples of the greeting, which is a karo in Yoruba. I did that. Then I now uploaded the dataset with unknown sounds, with hello world and noise inside. So the model will be able to differentiate different sounds. So this is just me clicking a sample and
Ẹ káàárọ̀,
that's one. So I'll go to a different one.
ẹ káàárọ̀,
So kind of different sounds, different frequencies. I use like high pitch, low pitch, and everything. So this is the impulse design. I created the added this. I really didn't change much. I adjusted in the first one. My accuracy kind of dropped, so leaving it like this was good. I used this 16,000 hertz for or 16 kilohertz for frequency. I used MFCC for audio, then classifier. I used MFCC for audio because it was better for this one was better for vocal, like human audio, not just any random sounds of sensors, like human voice. This one is better for human voices. Then classification. I use a classification model because I'm classifying between the greeting, noise, I'm classifying greeting, noise, and unknown sounds for any sample. So that's why I use classifier. Then going to MFCC, it kind of process the input features. Then we now add the spectrogram. So this is the spectrogram for the greeting. Then the spectrogram for the greeting is kind of similar, as you can see. So it's first greeting, this second greeting. So then this is the spectrogram for unknown sounds. Just unknown is not what we want. It's just random noises. And this is just some of the parameters that I used. I mostly left them defaults because I found out that defaults give me higher accuracy. Then for on device embedding, the peak RAM usage was 15 kilobytes, which was really good for a RAM enabled device. I'm going to go to the classifier. Now this is where my results for everything was after classifying. I left 100 epochs, learning rates was this, and I also added data augmentation, so it's to kind of improve the model, adding more noises, masking time bands, masking frequency bands, and all of that. Then this is the architecture. So there are the input layers here, the output layer, which are our four classes. That's noise, hello world, unknown sounds, and a car or the greeting. So that's our output. Then this is the hidden layers. So we could change and edit that. Then this is the metrics for everything. But first of all, looking at our accuracy was really high because we had a long time to record, like about 3 minutes. Although the other data, it would have been more accurate should I have recorded a longer and more diverse voice sample. So if I had more volunteers to give me different greetings, the accuracy would have gotten higher. But we see that when the actual label was the greeting, the predicted those greetings, we got this, and this is for when the actual label was written with predicted hello world just 6.3%. They did not predict written as noise at all, which is really good. And sometimes they had a bit of error predicting the greeting as noise, and we have the rest of that. Something similar. Then our F1 score 4%. This is kind of like the data explorer for everything. The red dots being the few errors around the board. And again, the on-device performance should we have choose to embed it. Then we moving on to our live classification. So let's just choose any at random. Just let's load the sample. so it's just taking a bit of time. But overall, this was a really good experience learning about models, learning about classification for audio samples. So it's created, so
ẹ káàárọ̀,
that's what it was. Then this was the results for it. So it assumed it to be greeting 37% and unknown because the if you notice the audio sample
ẹ
wasn't
káàárọ̀,
complete. It's a car it just cuts short. So this is kind of expected. This is what we want because the sample wasn't really correct. So loading another one, we'll see what we get. Hopefully this one will be a complete sound from beginning to end. I will see more positive prediction for the greeting. Job success, good. So this one,
ẹ ẹ káàárọ̀,
this was a complete greeting, very complete. And we noticed, wow, 99%. It did not even make any errors at all. I can see the MFCC confirming that it was a very
ẹ
complete from beginning
káàárọ̀,
to end, and this reflects. So just one more time, just to I'm taking at random, taking at okay, 18. I just go 18. Then let's classify that. Hopefully, we should see something similar to the second sample. That was 99% accurate. The the error was the unknown was 0%, noise was 0%, which was really good for a model of 93% accuracy. Right. So first of all, let's listen to it.
ẹ ká ẹ káàárọ̀,
Mm-hmm. Complete 93%, which is really accurate. So this is just my demonstration of the assignment given to me. But you thank you so much for this demonstration. Really appreciate you.